Howdy folks, Mr. Ree here, and welcome to one more question. So I'm going to be taking a look at solving another trig equation. This time the interior of the argument is going to have something that is not written in degrees, and as such, because it's unitless, is really written in radians. So we're going to solve this equation for a radian answer. So if you'd like to solve a trig equation with some medium type transformations to it, and do it for radians, you're in the right place. So let's get to it. All right, now, I like to write down what I'm working on, so I'm going to do that right away. Bet you didn't see that coming if you've seen other ones of my videos. Basically, I should probably just have it already written down, but I kind of get a satisfaction from writing it down as I do it. All right, so I have this particular equation. The reason I know I would like to give my answer in radians here is because I have a shift of pi over 4 without a degree symbol on it. So it means pi over 4 radians. So let's go ahead and just rearrange this for the trig statement, which is the tan of the argument stuff. So if I do that, I'm going to add 2 to both sides, which is going to give me 10 on the left. I'm going to divide both sides by 3, so I get 10 thirds, and that's going to be equal to the tan of 2 onto theta minus pi over 4. So there we go. We have the trig function isolated, and it's equal to 10 thirds, which doesn't ring a bell for anything that's supposed to be recognized by me here. So I'm going to take my calculator, I'm going to throw it into radian mode because I would like to have the answer in radians once it gives it to me, instead of having to convert it myself afterwards. So I'm going to take 10 divided by 3, the inverse tan of the left, because I'm also want to do the inverse tan of the right, which will undo the tan function and leave me with just that messy argument afterwards. So the left-hand side is the one I can't do without the calculator. So it's going to tell me I'm going to keep to the 1000th position. Not that that is a necessary thing, but I undo my tan, and I'm going to get, let's not use the bracket there, 2 onto theta minus pi over 4 is equal to, the calculator gives me 1.2793 technically, and as I said, I'm going to keep to the 1000th position, so I'm pretty happy with that. Now, we would also say that any full rotation of this, any of the coterminal angles would be acceptable. So I'm going to add on to that 2 pi k, where k is any integer. So 2 pi k, 2 pi is our untransformed size of the rotations there, 1 period. So that should give me my line of answers. Now, I'm going to get a second line of answers, but I'm actually going to solve for this one first. But don't let me forget about it. I have to recognize that the calculator gives me one answer, but there is a second answer because this is not the only location where tan is positive. We have another location within a single rotation from 0 to 2 pi radians, where tan will be positive. So we'll get to that in a moment. In the meantime, let me solve this for theta. So I'm going to divide both sides by 2. I should have kept maybe the unrounded value in there. So I'm going to round it according to my rounded value, which is probably a little bit of a sad story now, but it's 640. And then I divide my second thing also by 2, which will give me pi k. And so I'm left with theta minus pi over 4 is equal to that wonderful stuff there. Now, I'm going to actually use the exact value for the rotation part. So I'm going to keep it as a pi, at least for the time being. Maybe I'll change my mind later, but anyway, it is what it is. I am, however, going to use my calculator to take pi, which I'm just going to use 3.1415 divided by 4. And I'm going to add that to both sides of my equation. If I add that to the 0.640 and I round it to that same thousandths place, I'm going to get that theta is equal to 1.425 plus pi k. And again, the pi is a little bit suspicious here, because why would I need an infinite amount of precision when I've only kept to the thousandths position on my other value there? But I think it's a little tidier actually to just write pi k, and it's easier to recognize it as just being a kind of half of a rotation compared to normal, or half of a period compared to normal. It's a full rotation. Okay, so that's one of my lines of solutions. I needed to remember, thanks for reminding me, that there's another one here, and that other one is because tan is going to be positive when the y value and the x value divide to give you a positive ratio. So my y divided by x in quadrant 1, which is where this first 1.27 is, kind of something like that, positive divided by positive is a positive. Negative divided by negative is also a positive. So this one down here, which has the same reference angle in this location and in this location, is also going to give me that same value. So this is, if I went to this location right here, that would be pi, and I'm going to go that same reference angle further, which is 1.279 with that value. So I'm going to take pi, 3.1415, add on 1.279, and we will get that this is going to be at approximately 4.421, let's say. And full rotations from that, as long as we are making sure there are full rotations and not partial ones. This is our second line of solutions, so it's the entire argument that is equal to this. So all of the 2 onto theta minus pi over 4. I'm going to do the exact same thing that we did last time. Since I took the rounded value, I'm also going to take the rounded value this time, divide both sides by 2, and we'll end up with 2.211 plus pi k, where k is an element of our integer number system, and that we've divided this side by 2 as well, leaves me with just theta minus pi over 4. I'm going to take that pi, divide it by 4, add it to both sides of my equation, gets rid of it on the left. On the right, I'm going to end up having theta being equal to 2.996 plus pi k, where k is an element of our integer number system. So this combined with this should give us our full set of solutions for this particular trig equation. Again, I made this comment last time when I was doing it in degrees. If we wanted to, we could do the same question with the domain restriction. So only certain theta values are allowed in our final answer. If I did it that way, I would actually do everything the same up to this point, and then I would use test k values to try to figure out which answers are going to fit in the domain and which answers are not. So I would just use k is equal to 0, 1, 2, 3, and maybe negatives as well, depending on where my domain is, until I get values that are falling inside of my domain, and keep going until you get ones that fall outside of the domain, and only keep the ones that work. All right, so I like to, especially since I don't actually have any clue if this is the correct answer, other than I'm hoping I did the work right, I'm going to take my first line, which is going to be the 1.4. Actually, I like taking my second line because the calculator feeds you the first one. So I will take the second solution line, which is going to be 2.996 plus pi k. I'm going to choose a random k value. So I'm going to take negative 14 this time. So 2.996 plus pi, and I'm going to use random value. Oh, there's my button. I'll use the full thing. So pi times negative 14. So we'll go and get negative 40.986 radians. Now, I am going to sadly use the calculator value that just keeps a whole bunch of decimal places, just because it's going to be simple to do that without having to rewrite it. All right, so even though I have it rounded to the thousandth position for my 2.996, we'll see how this does. Let's go. So I take this value, I subtract from it pi over 4, and then I'm going to multiply that by 2. I'm going to take the tan of that particular value, and then I'm going to multiply that by 3, and then I'm going to subtract 2, and I'm supposed to get 8. I got 8.0099 if I round it to that next digit. So it is, we'll say within 1/100th of a unit. I'm pretty happy with that. I feel like that means my solution line is good, other than the fact that I was rounding values in order to make that up, and so it's going to be a little bit off of the exact value answer. So hopefully you found that to be a helpful exercise. So we were able to get a solution in radians for a trig equation that has some transformations built into it. So if you did find that one helpful, feel free to like and subscribe, comment if there's things that I could do better, and as always, take care, folks.